Right now, at this very moment, something extraordinary is happening to you. Something so fundamental, so deeply woven into the fabric of reality itself, that without it, you would not exist. Your body, your bones, your blood, the chair you are sitting on, the device you are watching this on, the air you are breathing, none of it would be here. I am not talking about gravity. I am not talking about electromagnetism. I am not talking about the nuclear forces that hold atoms together. I am talking about something far more mysterious. Something that fills every single point in the universe. Something that has no gaps, no holes, no empty spaces. It is everywhere. It is here. It is inside you. It is passing through you. And it is doing something to every single particle in your body right now, at this very second. Let me ask you a question that might sound strange. What gives things mass? You might say, well, things just have mass. A rock is heavy because it is made of heavy stuff. But here is the problem with that answer. At the most fundamental level, particles should not have mass. The mathematics of our universe, the equations that describe how everything works at the smallest scales, those equations say that particles should be massless. They should all be zipping around at the speed of light with no mass whatsoever. And yet, they do have mass. You have mass. The Earth has mass. Stars have mass. So where does it come from? What is giving mass to the fundamental building blocks of reality? The answer is one of the most mind-bending discoveries in the history of science. There is a field, an invisible, undetectable, omnipresent field that fills every cubic centimeter of the universe. And when particles move through this field, something happens to them. They gain mass. They slow down from light speed. They become the building blocks of atoms, molecules, stars, planets, and you. This field is called the Higgs Field. And today, we are going to take the deepest, most thorough dive into what this field actually is, how it works, what it is doing to every particle around you, and why without it, nothing in the universe would exist as we know it. But here is what makes this story truly incredible. For almost 50 years, this field was nothing more than a theoretical idea, a mathematical trick that seemed too elegant to be wrong, but too strange to be proven right. And then, in 2012, using the most expensive, most complex machine ever built by human civilization, scientists finally found the proof. They found the smoking gun. They found the Higgs Boson, the particle that confirms the existence of this field. And when that announcement was made, an 83-year-old physicist named Peter Higgs sat in the audience with tears streaming down his face, because the idea he had proposed nearly half a century earlier had finally been confirmed as real. This is not just a story about physics. This is a story about the nature of reality itself, about what it means to exist, about why anything has substance at all. And I promise you, by the end of this video, you will never look at the world the same way again. You will understand something profound about the universe that most people never learn in their entire lives. You will understand why you have mass, why you exist as a physical being, and why the universe is not just an empty void of massless particles flying around at the speed of light. Before we dive into this incredible journey, if you are someone who loves understanding the deepest mysteries of the universe, someone who gets excited by the idea that reality is far stranger than anything we could imagine, then hit that subscribe button right now. I want you to be part of this community of curious minds. Drop a comment below telling me, did you know that right now, as you watch this video, you are completely submerged in the Higgs field? And hit that like button, because this video represents months of research condensed into the deepest explanation you will find anywhere. Now, let us begin this journey from the very beginning. To understand the Higgs field, we first need to understand a crisis that shook the foundations of physics in the middle of the 20th century. By the early 1960s, physicists had built something remarkable. They had constructed what we now call the Standard Model of particle physics. This is essentially the rulebook of the universe at its smallest scale. It describes all the fundamental particles that exist and all the forces that act between them. It is, without exaggeration, the most successful scientific theory ever created. Its predictions have been verified to extraordinary precision. We are talking about predictions that match experiments to 12 decimal places. That is like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. But this incredible theory had a devastating flaw. A flaw so fundamental that it threatened to bring the whole thing crashing down. The problem was mass. You see, the mathematical framework of the Standard Model is built on something called gauge symmetry. This is a deep mathematical property that the equations must satisfy in order for the theory to be consistent, in order for it to make sensible predictions that do not produce nonsensical infinities. And here is the devastating problem. Gauge symmetry absolutely forbids particles from having mass. If you write down the equations with gauge symmetry, and then you try to simply add mass to the particles by hand, the whole mathematical framework breaks. The equations become inconsistent. They produce predictions that are nonsense, probabilities that are greater than 100%, physical quantities that are infinite. The theory self-destructs. But particles clearly have mass. The electron has mass. The quarks inside protons and neutrons have mass. The W and Z bosons that carry the weak nuclear force have mass. This was not a small discrepancy. This was a fundamental contradiction between what the math said should be true and what experiments clearly showed was true. The math said particles must be massless. Reality said they clearly are not. Something was deeply wrong. Either the beautiful mathematical framework was incorrect, or there was some hidden mechanism, some missing piece of the puzzle that could give particles mass without breaking the sacred gauge symmetry. This was the crisis. This was the problem that kept theoretical physicists awake at night in the 1960s. The Standard Model was too successful to be wrong. Its predictions were too accurate. Its mathematical structure was too elegant. But it could not account for the most obvious property of matter, the fact that it has mass. Something had to give. And what provided the solution was one of the most brilliant ideas in the history of physics. In 1964, several groups of physicists independently proposed a radical solution. Peter Higgs in Edinburgh, Robert Brout and François Englert in Brussels, Gerald Guralnik, Carl Hagen, and Tom Kibble in London. They all arrived at essentially the same idea from different angles. And the idea was this: what if there is a field that permeates all of space? A field unlike any other field we know. A field that has a peculiar, unique property. Unlike every other known field in the universe, this field has a non-zero value even in completely empty space. Even in a perfect vacuum, even when nothing is happening. This field is always there, always on, always at a constant non-zero value throughout the entire universe. And here is the key insight. When particles interact with this ever-present field, this interaction behaves mathematically exactly like mass. The particles are not born with mass. They acquire it through their interaction with this field. Particles that interact strongly with the field gain a lot of mass. Particles that interact weakly gain only a little mass. And particles that do not interact with the field at all remain massless. The beauty of this mechanism is that it gives particles mass without breaking gauge symmetry. The underlying equations remain symmetric. The symmetry is just hidden, disguised by the non-zero value of this omnipresent field. This was the proposal. This was the theoretical prediction. And for almost half a century, it remained unproven. A beautiful mathematical idea that might or might not correspond to reality. But before we get to the incredible story of how it was finally proven, we need to understand something more fundamental. We need to understand what a field actually is in physics. Because without understanding fields, you cannot truly understand what the Higgs field is or what it is doing. When physicists talk about a field, they mean something very specific. A field is simply a quantity that has a value at every point in space and time. Let me give you an everyday example. Think about temperature. At every point in this room, there is a temperature. Near the window, it might be cooler. Near a heater, it might be warmer. But at every single point, there is a definite temperature value. Temperature fills the room. It does not have gaps. There is no point in the room where temperature simply does not exist. This is what we mean by a field. It is something that exists everywhere, with a value at every point. Now, in physics, the important fields are far more fundamental than temperature. The electromagnetic field exists at every point in the universe. At every location, you can ask, what is the strength and direction of the electric field here? And what is the strength and direction of the magnetic field here? This field is what light is made of. When the electromagnetic field vibrates, those vibrations are what we call photons, what we call light. The gravitational field exists at every point as well. It tells objects how to curve their paths through space. But here is where it gets really deep. In modern physics, in the framework we call quantum field theory, we have learned something extraordinary. Every type of particle in the universe is actually a vibration, an excitation, a ripple in its corresponding field. Think about that for a moment. Electrons are not little balls flying around. An electron is a vibration in the electron field. A vibration in a field that permeates all of space. Quarks are vibrations in the quark field. Photons are vibrations in the electromagnetic field. Every particle you have ever heard of is actually a ripple in an underlying field that fills the universe. So when you look at your hand, what are you really seeing? You are seeing trillions upon trillions of vibrations in various quantum fields. Vibrations in the electron field. Vibrations in the quark fields. These vibrations interact with each other, bind together, form atoms, form molecules, form cells, form your hand. Reality at its deepest level is not made of particles at all. It is made of fields, and particles are just the way those fields manifest when they vibrate. Now, here is what makes the Higgs field unique among all these fields. Every other quantum field in the universe has a value of 0 in its ground state, meaning in empty space, when nothing is happening, when no particles are present. Every other field is at 0. The electron field is at 0. The quark field is at 0. The electromagnetic field is at 0. They are all sitting quietly at nothing. But the Higgs field is different. In its ground state, in empty space, in a perfect vacuum with absolutely nothing in it, the Higgs field has a constant non-zero value. Everywhere, throughout the entire universe. This value is approximately 246 billion electron volts. This is not zero. This is a substantial, constant, ever-present value. And this is what changes everything. This ever-present, non-zero value is what gives particles their mass. Particles moving through the universe are constantly immersed in this non-zero Higgs field. And depending on how strongly they couple to this field, they acquire different amounts of mass. It is as if the entire universe is soaked in this invisible substance, and particles swimming through it pick up mass depending on how much this substance sticks to them. Now, I need to be very careful here with analogies, because the most common analogies for the Higgs mechanism can be misleading if taken too literally. You have probably heard the famous analogy of a celebrity walking through a crowded room. The idea is that the celebrity is like a particle, and the crowd of people is like the Higgs field. As the celebrity tries to walk through the room, people cluster around them, slowing them down, making it harder for them to move. This clustering is supposed to represent the acquisition of mass, and a less famous person can walk through the same room with less interference, representing a lighter particle. This analogy captures something true. It captures the idea that different particles interact with the Higgs field with different strengths. But it is misleading in a crucial way. It suggests that the Higgs field creates a kind of friction, a kind of drag that slows particles down. This is absolutely not what happens. In reality, a massive particle moving at a constant speed through the Higgs field experiences no resistance whatsoever. It does not slow down, it does not lose energy, there is no friction. So what does the Higgs field actually do? What does it mean to give something mass? Here is the key. Mass is not about being slowed down. Mass is about inertia. Mass is about how hard it is to change something's state of motion. A bowling ball is hard to push, not because something is creating friction against it, but because it resists changes in its motion. That resistance to acceleration, that is what mass is. And that is what the Higgs field gives to particles. It gives them inertia. It gives them resistance to acceleration. Think of it this way. A massless particle, like a photon, has no inertia at all. The moment it is created, it is already moving at the speed of light. It cannot move at any other speed. It has zero resistance to motion because it has zero mass. But a particle that couples to the Higgs field, like an electron, gains inertia. It resists being pushed. It takes force to accelerate it. It can move at different speeds. And the stronger its coupling to the Higgs field, the more inertia it has, the heavier it is, the harder it is to push. Let me now describe the actual mechanism more precisely, because this is where it gets truly fascinating. In quantum field theory, a massless particle moves through space in a particular way. It flips between different types as it moves. For particles like the electron, which has a property called chirality, the massless version would flip between what physicists call left-handed and right-handed states as it propagates. But here is the thing. In the standard model, the left-handed electron and the right-handed electron are actually different particles. They interact with forces differently. The left-handed electron feels the weak nuclear force. The right-handed electron does not. They are fundamentally different objects. Now, what the Higgs field does is remarkable. Because the Higgs field has a constant non-zero value everywhere, it acts as a medium that allows these left-handed and right-handed states to talk to each other, to convert into each other. Every time a left-handed electron encounters the Higgs field, it can convert into a right-handed electron, and then back again. This constant back and forth, this constant flipping between left and right, mediated by the ever-present Higgs field, is what creates the appearance of mass. The particle is essentially bouncing back and forth between two massless states, and this bouncing, this interaction with the Higgs field at every point in space, is what we observe as a massive particle with inertia. This is not just an analogy. This is literally what is happening at the quantum level. The strength of this coupling, how easily the particle flips between left and right by interacting with the Higgs field, determines how massive the particle appears to be. The top quark, the heaviest known fundamental particle, flips extremely rapidly because its coupling to the Higgs field is extremely strong. The electron flips much less rapidly because its coupling is much weaker. And the photon does not flip at all because it does not couple to the Higgs field whatsoever. Now, let us go deeper. Let us understand how the Higgs field ended up with this non-zero value in the first place. Because fields do not just randomly decide to have non-zero values. Something must have caused this. And the answer takes us all the way back to the very beginning of the universe, to a fraction of a second after the Big Bang. The concept we need to understand is called spontaneous symmetry breaking. And despite the intimidating name, the core idea is actually quite intuitive when explained properly. Let me paint a picture for you. Imagine you have a bowl shaped like a Mexican hat or a sombrero. The top of the hat is a high point in the center, and all around the brim there is a circular valley, a ring of low points, all at the same height. Now imagine placing a ball perfectly at the very top of this hat. At the top, the situation is perfectly symmetric. Every direction looks the same from the center. There is no preferred direction. The ball is balanced. But here is the crucial point. This position, while symmetric, is unstable. The slightest nudge will cause the ball to roll down off the center and into the valley of the brim. Once it does this, symmetry is broken. The ball is now sitting at one particular point on the brim, which picks out one particular direction. The underlying shape is still symmetric, the brim is still circular, but the ball's position has broken that symmetry. This is exactly what happened to the Higgs field in the early universe. The mathematics of the Higgs field gives it an energy landscape that looks exactly like this Mexican hat shape. The height represents energy. The position of the ball represents the value of the Higgs field. In the very early universe, when temperatures were astronomically high, the Higgs field was sitting at the center, at the top of the hat. Its value was zero everywhere. The universe was symmetric. All particles were massless. Everything was moving at the speed of light. But as the universe expanded and cooled, this position became unstable. The Higgs field, like that ball on top of the hat, had to roll down into the valley. It had to find a lower energy state. And when it did, its value went from zero to that non-zero value of 246 billion electron volts. This transition happened approximately 1 trillionth of a second after the Big Bang. 1 trillionth of a second. In that unimaginably brief moment, the nature of reality changed forever. Particles that had been massless and flying around at the speed of light suddenly gained mass, suddenly gained inertia, suddenly became able to slow down, to be captured, to bind together. In that 1 trillionth of a second, the possibility of atoms, molecules, stars, planets, and life was born. This event is called the Electroweak phase transition. And the word phase transition is deliberate. It is the same concept as water freezing into ice. When water freezes, the random symmetric arrangement of water molecules suddenly locks into a structured crystal lattice. Symmetry is broken. The liquid phase is the same in every direction, but the ice crystal picks out specific directions in its lattice structure. In the same way, when the universe cooled below a critical temperature, the Higgs field froze into its current non-zero state. And the symmetry that existed before was broken. But what symmetry was broken exactly? This is where the story becomes truly profound. Before the Electroweak phase transition, before the Higgs field acquired its non-zero value, the electromagnetic force and the weak nuclear force were not two separate forces. They were one unified force called the Electroweak force. The photon and the W and Z bosons were all part of the same family, all massless, all behaving in a unified way. But when the Higgs field switched on, when it acquired its non-zero value, this unity was shattered. The W and Z bosons gained enormous masses from their interaction with the Higgs field. The photon remained massless because it does not couple to the Higgs field. And suddenly, what had been one force became two very different forces with very different properties. The electromagnetic force carried by the massless photon became a long-range force that can reach across the entire universe. This is why light from distant galaxies can reach your eyes. This is why magnets work. This is why electricity flows through wires. The photon has no mass, so the electromagnetic force has infinite range. But the weak nuclear force, now carried by the massive W and Z bosons, became a short-range force, limited to distances smaller than the size of an atomic nucleus. Why? Because massive particles are expensive to create. The uncertainty principle of quantum mechanics allows force-carrying particles to exist briefly as virtual particles, but the more massive they are, the shorter the time they can exist, and the shorter the distance they can travel. The W boson has a mass about 80 times that of a proton. The Z boson has a mass about 91 times that of a proton. These are incredibly heavy particles. And because they are so heavy, they can only travel tiny distances before they must disappear. This is why the weak force only operates over extremely short ranges. Think about the implications of this. If the Higgs field did not exist, if it had never acquired its non-zero value, the W and Z bosons would be massless like the photon. The weak force would be a long-range force like electromagnetism. Radioactive decay would work completely differently. The nuclear reactions inside stars would be unrecognizable. The sun would not shine the way it does. The elements would not have been forged in the way they were. You would not be here. Now, let us talk about the discovery itself. Let us talk about how humanity actually proved that this field exists. Because remember, for almost 50 years, the Higgs field was just a theory, a mathematical construction, an elegant idea. But science does not accept ideas just because they are elegant. Science demands evidence. And finding evidence for the Higgs field required building the most extraordinary machine in human history. The logic was simple in principle. If the Higgs field exists, then like every other quantum field, it should be possible to create vibrations in it. Excitations, ripples, and just as a ripple in the electromagnetic field is a photon, a ripple in the Higgs field should be a particle, the Higgs boson. If you could create a Higgs boson, detect it, measure its properties, that would be proof that the Higgs field exists. But creating a Higgs boson requires an enormous amount of energy. The Higgs field is very stiff in a sense. It takes a lot of energy to disturb it, to create a ripple in it. You need to concentrate an enormous amount of energy into a tiny point. And the way physicists concentrate energy is by accelerating particles to nearly the speed of light and smashing them together. All that kinetic energy, all that motion energy, gets converted into new particles, according to Einstein's famous equation relating energy and mass. If you can concentrate enough energy, you can create particles that are much heavier than the ones you started with. This is where the Large Hadron Collider comes in. The LHC, located at the European Organization for Nuclear Research, known by its French acronym CERN, near Geneva, Switzerland. This machine is not just a scientific instrument. It is arguably the most complex and ambitious construction project in human history. Let me give you a sense of its scale. The LHC is a circular tunnel, 27 kilometers in circumference. That is about 17 miles. If you tried to walk around it, it would take you about 5 to 6 hours. It sits between 100 and 175 meters underground, beneath the border region between Switzerland and France. Inside this tunnel are 2 beam pipes, each containing a beam of protons traveling in opposite directions. These protons are accelerated by powerful electric fields and steered by over 1,700 superconducting magnets cooled to minus 271 degrees Celsius, colder than outer space. The protons in each beam are organized into bunches, about 100 billion protons per bunch. And these bunches are spaced so that they cross each other about 40 million times per second at 4 points around the ring. At those crossing points sit enormous detectors, cathedral-sized instruments designed to detect and measure the particles produced in the collisions. The two main detectors are called ATLAS and CMS, and each one is an engineering marvel involving thousands of physicists from dozens of countries. When these proton beams are at full energy, each proton carries an energy of 7 trillion electron volts, and it is moving at 99.999999% of the speed of light. When two such protons collide head-on, the total collision energy is 14 trillion electron volts. This is an enormous amount of energy concentrated into a space smaller than an atomic nucleus. And in that tiny point of concentrated energy, new particles are born, including, if you are lucky, the Higgs boson. But here is the challenge. The Higgs boson is incredibly rare and incredibly short-lived. Out of the roughly 1 billion proton-proton collisions that happen every second at the LHC, only about 1 in 10 billion produces a Higgs boson. And even when a Higgs boson is produced, it exists for an almost impossibly brief time. Its lifetime is approximately 1.6 times 10 to the power of minus 22 seconds. That is 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000And it is those decays, transforming into other particles. And it is those decay products that the detectors actually observe. The physicists never see the Higgs boson itself. They see what it leaves behind. They see pairs of photons, or pairs of Z bosons, or pairs of W bosons, or pairs of bottom quarks, flying out from the collision point. And they must work backwards from these decay products to reconstruct what created them. It is like hearing an explosion and trying to determine what kind of bomb it was from the pattern of debris. Only far, far more complex. Finding the Higgs boson was not a matter of seeing one clear event. It was a matter of statistics. You have to look at millions and millions of collisions, carefully measure the energies and momenta of the particles produced, and look for a tiny excess, a slight bump in the data that cannot be explained by any other known process. This requires extraordinary precision. It requires understanding your detector perfectly. It requires accounting for every possible background process that could mimic the signal you are looking for. The search took years. Thousands of physicists working around the clock, analyzing petabytes of data, running simulations, checking and rechecking their results. And then, on July 4, 2012, at a packed seminar at CERN, the results were announced. Both ATLAS and CMS, working independently, had found a new particle with a mass of approximately 125 billion electron volts. The statistical significance of the signal was 5 sigma, meaning the probability that this was a random fluctuation rather than a real particle was about 1 in 3.5 million. In particle physics, 5 sigma is the gold standard for discovery. It was real. The Higgs boson existed. The Higgs field was real. The room erupted in applause. Physicists who had devoted their entire careers to this search were in tears. And in the audience sat Peter Higgs, 83 years old, watching his prediction from 1964 finally confirmed by experiment. He wiped tears from his eyes. Nearly half a century of waiting, nearly half a century of hoping that nature actually worked the way he had proposed. And it did. The following year, in 2013, Peter Higgs and François Englert were awarded the Nobel Prize in Physics for their theoretical prediction. Robert Brout, who had worked with Englert, had sadly passed away in 2011, just a year before the discovery. And Nobel Prizes are not awarded posthumously. Now, let me take you into something truly fascinating and somewhat unsettling about the mass of the Higgs boson. The measured mass, approximately 125 billion electron volts, seems like just a number. But this specific number has profound implications for the fate of the universe itself. You see, physicists have calculated what the universe's vacuum, the empty space in which we live, looks like in terms of energy stability, and the result depends sensitively on two numbers, the mass of the Higgs boson and the mass of the top quark. With the measured values, our universe appears to be in a state called metastability. This is not the most stable possible state. It is like a ball resting in a small depression on the side of a hill. It is stable for now. Small disturbances will not knock it out. But it is not at the bottom of the hill. There exists a lower energy state that the universe could potentially transition to. What would this mean? In quantum mechanics, there is a phenomenon called quantum tunneling, where a system can spontaneously transition from one state to another, even if there is an energy barrier in the way. It is extremely improbable for large systems, but it is not impossible. If the Higgs field were to quantum tunnel from its current value to the deeper, more stable minimum, the consequences would be catastrophic beyond imagination. A tiny bubble of the new, lower energy vacuum would form, and this bubble would expand outward at the speed of light. Inside this bubble, the Higgs field would have a different value. Particles would have different masses. The laws of physics as we know them would be different. Atoms as we know them could not exist. Chemistry could not exist. Life could not exist. The bubble would sweep outward in all directions at light speed, and everything it touched would be instantly transformed into something completely alien. You would never see it coming, because it travels at the speed of light. There would be no warning, no escape, no survival. Now, before you panic, let me emphasize something crucial. The probability of this happening is extraordinarily low. The expected time for such a tunneling event is estimated to be far, far longer than the current age of the universe. We are talking about timescales that make the current 14 billion-year age of the universe look like the blink of an eye. So this is not something you need to lose sleep over tonight. But the philosophical implication remains striking. Our universe may not be in its final, most stable state. We may be living in a temporary condition that will eventually change, even if eventually means timescales we can barely comprehend. There is also an important caveat. These calculations depend on our current understanding of physics. If there are new particles or new forces that we have not yet discovered, particles that exist beyond the standard model, they could change this calculation entirely. They could stabilize the vacuum and make our universe absolutely stable. We simply do not know yet. This is one of the many reasons why physicists continue to search for physics beyond the standard model. Now I want to address something that is extremely important and that many people get wrong about the Higgs field. I have told you that the Higgs field gives particles their mass, and that is true. But here is the twist. The Higgs field is not responsible for most of the mass you see around you. Let me explain. Look at yourself. Your body is made of atoms. Those atoms are mostly hydrogen, carbon, nitrogen, and oxygen. Each atom has a nucleus made of protons and neutrons, surrounded by electrons. The electrons get their mass from the Higgs field. That part is straightforward. The electron couples to the Higgs field, and this coupling gives the electron its mass of about 500,000 electron volts. But the electron is incredibly light compared to the nucleus. The mass of an atom is almost entirely in its nucleus, in its protons and neutrons. A proton has a mass of about 938 million electron volts. Now, a proton is made of 3 quarks, 2 up quarks and 1 down quark. The up quark has a mass of about 2 million electron volts, and the down quark has a mass of about 5 million electron volts. These quark masses come from the Higgs field. But wait, 2 up quarks plus 1 down quark gives you about 9 million electron volts. The proton's mass is 938 million electron volts. The quarks account for barely 1% of the proton's mass. Where does the other 99% come from? The answer is absolutely beautiful. It comes from energy. Specifically, it comes from the kinetic energy of the quarks bouncing around inside the proton, and from the energy stored in the strong force fields, the gluon fields, that bind the quarks together. Remember Einstein's famous equation, E equals mc²? It can be read in reverse. Not just mass can be converted to energy, but energy can manifest as mass. The enormous amount of energy contained in the strong force interactions inside a proton, that energy shows up as mass. The proton is heavy, not because its quarks are heavy, but because its quarks are furiously bouncing around at near light speed, held together by incredibly strong gluon fields. And all that energy manifests as mass. So when you step on a scale, about 99% of the mass your scale registers comes from the strong force energy inside your protons and neutrons, not from the Higgs field. Only about 1% comes from the Higgs mechanism, giving mass to the quarks and electrons. This is a remarkable fact. Most of your mass is not given to you by the Higgs field. Most of your mass is actually the energy of the strong nuclear force, frozen into the form of matter by Einstein's famous equation. But does this mean the Higgs field is unimportant for your existence? Absolutely not. Remember, without the Higgs field, electrons would be massless. Massless electrons cannot be captured into atomic orbits. Without electron orbits, there are no atoms. Without atoms, there is no chemistry. Without chemistry, there is no life. So while the Higgs field is not directly responsible for most of your mass, it is absolutely essential for the existence of atoms, and therefore for your existence. Furthermore, without the Higgs field giving mass to the W and Z bosons, the weak force would behave completely differently, and the nuclear reactions that power stars and create the elements necessary for life would not work as they do. Let me also address another common misconception. The Higgs boson is often called the God particle in popular media. This nickname originally came from the title of a book by physicist Leon Lederman, published in 1993. But here is the thing Lederman actually wanted to call it. He wanted to call it the goddamn particle because it was so difficult to find. His publisher changed it to the God particle because that sounded more marketable. Most physicists actually dislike this nickname intensely. It gives the false impression that the Higgs boson is somehow more fundamental or more important than other particles. It is not. It is an important piece of the puzzle, certainly, but it is not more divine or special than, say, the electron or the photon. The nickname is misleading, and physicists generally prefer to simply call it the Higgs boson. Now let us explore something truly mind-bending. Let us think about what would happen if the Higgs field simply disappeared. If, somehow, the Higgs field's value dropped to 0 throughout the universe, what would the consequences be? This thought experiment reveals just how central the Higgs field is to the structure of reality. The very first thing that would happen is that all fundamental particles that gain mass from the Higgs field would become massless. Electrons, quarks, the W and Z bosons, all massless in an instant. Now think about what this means for atoms. Atoms exist because electrons are captured in orbits around nuclei by the electromagnetic force. The electrons stay in these orbits because they have mass, because they can move at speeds less than light, because they have inertia. A massless electron cannot orbit anything. A massless electron must move at the speed of light in straight lines. The electromagnetic force can still deflect it, but it cannot bind it. Every atom in the universe would instantly disintegrate as electrons flew away at light speed. But it gets worse. The quarks inside protons and neutrons would also become massless. Now, interestingly, the proton would still have most of its mass. Because remember, most of the proton's mass comes from strong force energy, not from quark masses. But the properties of the quarks would change so dramatically that the internal dynamics of the proton would be altered. More importantly, without the mass difference between up quarks and down quarks. Protons and neutrons would become essentially interchangeable, which would radically alter nuclear physics. The most dramatic change, however, would be to the W and Z bosons. Without their Higgs-given masses, they would become massless, like the photon. The weak force would no longer be weak or short range. It would become a long-range force, just like electromagnetism. In fact, it would merge back with electromagnetism into the unified electroweak force. Radioactive decay would happen much faster and over much longer distances. Every neutron would decay almost instantly. Nuclei would be unstable. Matter as we know it could not exist. So in a universe without the Higgs field, there would be no atoms, no molecules, no chemistry, no solid objects, no liquids. No gases, no stars, no planets, no life. Everything would be reduced to a soup of massless particles flying around at the speed of light, unable to form any kind of structure. The universe would be formless, featureless, and devoid of complexity. Structure requires mass. Complexity requires mass. Life requires mass. And mass, at the fundamental level, requires the Higgs field. But here is something even more subtle and fascinating. The specific value of the Higgs field, that 246 billion electron volts, is not arbitrary. If this value were different, even by a relatively small amount, the universe would be radically different. If the Higgs field value were much larger, all particles would be much heavier. Nuclear physics would change. Stars might not form, or they might burn so quickly that planets could never develop. If the Higgs field value were much smaller, particles would be much lighter, and again, the specific nuclear reactions and chemical bonds that we depend on might not work. This raises one of the deepest questions in all of physics. Why does the Higgs field have the value it does? Why 246 billion electron volts and not some other number? Why is it tuned to a value that allows atoms, chemistry, stars, planets, and life to exist? This is part of the broader fine-tuning problem in physics, and it remains one of the greatest unsolved mysteries. Some physicists believe there must be a deeper theory that explains this value. Others invoke the anthropic principle, arguing that in a multiverse of many different universes with different Higgs field values, we naturally find ourselves in one that allows our existence because we could not exist in the others. This debate is ongoing and may not be resolved for decades or even centuries. Now, let me take you into an even deeper mystery. The hierarchy problem. This is considered by many physicists to be the most important unsolved problem in fundamental physics, and it is directly related to the Higgs boson. Here is the problem. In quantum field theory, the mass of a particle is not simply a fixed number. It receives corrections from virtual particles, the quantum fluctuations that constantly bubble in and out of existence in the vacuum. These corrections affect every particle, but for the Higgs boson, they are particularly problematic. The quantum corrections to the Higgs boson mass are sensitive to the highest energy scales in physics. If there is new physics at some high energy scale, say at the Planck scale, where quantum gravity becomes important, then the Higgs mass should receive corrections that are proportional to that high scale. The Planck scale is approximately 10 to the power of 19 billion electron volts. The Higgs mass is 125 billion electron volts. That is a difference of 17 orders of magnitude. The natural expectation from quantum field theory is that the Higgs mass should be pushed up to near the Planck scale by these quantum corrections. The fact that it is so much lighter, 17 orders of magnitude lighter, seems to require an almost miraculous cancellation between different contributions. It is like balancing a checkbook, where the income and expenses are both in the quadrillions of dollars, but they happen to cancel out to leave a balance of just $125. Possible, but incredibly unlikely without some explanation. This is the hierarchy problem. Why is the Higgs mass so much smaller than the natural scale of physics? Why is there such a vast hierarchy between the Electroweak scale and the Planck scale? And is there a mechanism that naturally keeps the Higgs mass light? Several solutions have been proposed over the decades. The most popular for many years was supersymmetry, often abbreviated as SUSY. Supersymmetry proposes that every known particle has a heavier partner particle with different spin properties. These partner particles would contribute to the quantum corrections of the Higgs mass with the opposite sign, naturally cancelling out the dangerous large contributions and keeping the Higgs mass light. It is an elegant mathematical solution that also has other attractive features, such as providing a candidate for dark matter and enabling the unification of all three forces at high energies. For decades, supersymmetry was the leading candidate for physics beyond the Standard Model. Many physicists expected the LHC to discover supersymmetric partner particles shortly after it began operations. But years of searching have found nothing. No supersymmetric particles have been detected. The simplest versions of supersymmetry have been ruled out. More complex versions remain possible, but are increasingly contrived. This has created something of a crisis in theoretical particle physics. Other proposed solutions include extra dimensions of space. In theories with extra spatial dimensions, gravity might be diluted because it spreads into dimensions that other forces cannot access. This could explain why gravity is so much weaker than the other forces and could address the hierarchy problem. But again, no experimental evidence for extra dimensions has been found. Some physicists have proposed that the Higgs mass might be explained by the multiverse, the idea that our universe is one of an enormous number of universes with different physical constants, and we simply find ourselves in one where the Higgs mass happens to take a value compatible with our existence. This is philosophically controversial because it may not be testable. And some physicists have proposed even more radical ideas, such as the relaxation mechanism, where the Higgs mass is set dynamically by the cosmological evolution of a new field. Or the idea that the hierarchy problem is simply how the universe is, and there is no deeper explanation. The honest answer, as of today, is that we do not know. The hierarchy problem remains unsolved. Let me now take us in a different direction and explore how the Higgs field connects to the very origin and fate of the universe. This brings us to cosmology, the study of the universe on its largest scales and longest timescales. We talked earlier about the Electroweak phase transition, the moment when the Higgs field acquired its non-zero value about 1 trillionth of a second after the Big Bang. But there are deeper questions here. Was this phase transition smooth or violent? Did it happen gradually or suddenly? The answer to this question has enormous implications for our understanding of the universe. If the phase transition was first order, meaning it happened suddenly, like water turning to ice, then it would have produced bubbles of the new phase nucleating and expanding within the old phase. These bubbles would collide and merge, releasing enormous amounts of energy. This violent, turbulent process could have produced gravitational waves, ripples in space-time itself, that might still be detectable today. Several proposed future experiments, including space-based gravitational wave detectors, might be able to detect these primordial gravitational waves, and thus tell us about the nature of the electroweak phase transition. A first-order electroweak phase transition is also interesting for another reason. It could help explain one of the biggest mysteries in cosmology, the matter-antimatter asymmetry. Our universe is made almost entirely of matter, but the Big Bang should have produced equal amounts of matter and antimatter. What happened to the antimatter? How did the universe end up with a slight excess of matter? One possible answer involves the electroweak phase transition. If this transition was violent enough, if it produced enough departure from thermal equilibrium, it might have created the conditions necessary for processes that violate the symmetry between matter and antimatter. This is an active area of research, and the Higgs field is at its center. There is also a fascinating connection between the Higgs field and cosmic inflation. Inflation is the theory that the universe underwent a brief period of extremely rapid expansion in its earliest moments, expanding by a factor of at least 10 to the 26th power in a fraction of a second. This expansion explains why the universe is so flat, so uniform, and so large. Inflation is driven by a field called the inflaton field, and some physicists have proposed that the Higgs field itself could have played this role. The idea, called Higgs inflation, proposes that in the very early universe, when the Higgs field was at large values, it could have driven inflationary expansion before settling down to its current value. This is a speculative but mathematically viable idea that connects the Higgs field to the very birth of the observable universe. There is yet another connection between the Higgs field and cosmology, and this one involves one of the biggest embarrassments in all of theoretical physics: the cosmological constant problem. Observations tell us that the expansion of the universe is accelerating. Something is pushing space apart, making distant galaxies recede from us ever faster. We call this mysterious something dark energy, and it behaves like a constant energy density filling all of space. Now, quantum field theory predicts that the vacuum, empty space, should have an energy density. Every quantum field contributes to this vacuum energy, and the Higgs field, with its non-zero value, contributes as well. When you calculate the expected vacuum energy from quantum field theory, you get a number that is roughly 120 orders of magnitude larger than what we observe, one followed by 120 zeros times too large. This is perhaps the worst prediction in the history of physics. The observed value of the cosmological constant is not zero, but it is incredibly tiny compared to what theory expects. Why is the vacuum energy so small? Why does it not have the enormous value that quantum field theory predicts? This is the cosmological constant problem, and it is deeply connected to the Higgs field because the Higgs contributes to this vacuum energy through its non-zero field value. Solving this problem may require a revolution in our understanding of quantum field theory, gravity, or both. Now let me take you into the current state of Higgs physics. What have we learned since the discovery in 2012, and what are we still trying to learn? Since the discovery, the LHC has produced millions of Higgs bosons and studied their properties in great detail. Every measurement so far is consistent with the standard model prediction. The Higgs boson decays into pairs of particles with exactly the rates predicted by theory. It is produced in collisions with exactly the rates predicted by theory. Its spin and parity, technical quantum properties, are exactly as the standard model predicts. In short, the Higgs boson we found looks exactly like the one predicted by the simplest version of the Higgs mechanism. But there are many things we still do not know. One of the most important is the Higgs self-coupling. You see, the Higgs boson should interact with itself. Just as it gives mass to other particles, the Higgs field also gives mass to the Higgs boson itself. This self-interaction determines the shape of the Higgs potential, that Mexican hat shape we discussed earlier. Measuring the Higgs self-coupling would tell us the exact shape of this potential and could reveal whether our vacuum is truly metastable or absolutely stable. But measuring the self-coupling requires producing two Higgs bosons simultaneously, which is an extremely rare process. About 1,000 times rarer than producing a single Higgs boson. The LHC is working toward this measurement, but it may require the planned high luminosity upgrade, which will increase the collision rate by a factor of 10. Another open question is whether the Higgs boson couples to particles in a way that might reveal new physics. Does it decay into unexpected particles? Does it decay into dark matter? Current measurements have not shown anything unexpected, but the precision is still limited. As more data is collected and the measurements become more precise, any deviation from standard model predictions could be the first sign of new physics. There are also proposals for future colliders that could study the Higgs in even more detail. The proposed future circular collider at CERN would be a 100-kilometer circumference machine, nearly 4 times the size of the LHC. In its first phase, it would collide electrons with positrons at energies optimized for producing Higgs bosons, essentially functioning as a Higgs factory. This would allow precision measurements of Higgs properties to a level far beyond what the LHC can achieve. In its second phase, it would collide protons at energies of 100 trillion electron volts, 7 times higher than the LHC, which could reveal new particles and new physics. Other proposed machines include the International Linear Collider in Japan, the Circular Electron-Positron Collider in China, and the Cool Copper Collider in the United States. All of these have studying the Higgs boson as a central goal. The next decades of particle physics will be largely shaped by our desire to understand the Higgs sector more deeply. Let me now explore a possibility that pushes beyond the standard model. What if there is not just one Higgs field, but multiple? The standard model has the simplest possible Higgs sector, a single Higgs field that produces one Higgs boson. But there is nothing in principle that prevents nature from having a more complex Higgs sector. In fact, many extensions of the standard model predict additional Higgs bosons. Supersymmetry, for example, requires at least 5 Higgs bosons, 2 charged ones and 3 neutral ones. The one we found at 125 billion electron volts could be just the lightest of these 5. The others could be heavier and have not yet been produced at the LHC because we do not have enough energy. Other models predict Higgs bosons that are lighter than the one we found, but interact very weakly with ordinary matter, making them hard to detect. Some models predict Higgs bosons that couple to dark matter particles, potentially providing a portal between the visible universe and the dark sector. The Higgs could be our window into an entire hidden world of particles that we have not yet detected. This idea of the Higgs as a portal to dark matter is particularly exciting. Dark matter makes up about 27% of the total energy content of the universe, far more than ordinary matter, yet we have never directly detected it. We know it exists because of its gravitational effects on galaxies and on the large-scale structure of the universe. But we do not know what it is made of. If dark matter particles interact with the Higgs field, then Higgs bosons produced at the LHC could occasionally decay into dark matter particles. These events would show up as missing energy in the detector, because the dark matter particles would escape without being detected. Searches for such events are ongoing, and while nothing has been found yet, the sensitivity continues to improve with more data. Now I want to take a step back and talk about something philosophical but deeply important. What does the Higgs field tell us about the nature of reality? What does it mean that mass, this seemingly fundamental property of matter, is not intrinsic, but is acquired through interaction with a field? Before the Higgs mechanism was understood, you might have thought of mass as a basic, irreducible property of a particle. An electron just is a certain mass. It has that mass as an inherent property, the same way it has a certain electric charge. But the Higgs mechanism tells us something different. It tells us that mass is relational. Mass emerges from a relationship between a particle and the Higgs field. The electron does not carry its mass in some internal pocket. It gains its mass from its coupling to the field that permeates all of space. Take away the field, and the mass vanishes. This is a profound shift in how we think about properties of matter. It suggests that what we see as intrinsic might actually be emergent. What seems fundamental might actually arise from deeper relationships. This echoes a broader theme in modern physics. Many properties that seem basic, solid, permanent, turn out to be emergent phenomena arising from more fundamental underlying structures. Think about it this way. You are sitting there, a being made of matter, and that matter has mass, and that mass gives you weight on this planet, holds you in your chair, gives you solidity and substance. But at the deepest level, that mass is not yours in any fundamental sense. It is being continuously generated by your interaction with an invisible field. You are, in a very real sense, being continuously created by the Higgs field. Every moment of your existence, every second of your life, the Higgs field is actively giving mass to the quarks and electrons that compose you. If it stopped, even for an instant, you would cease to exist as a physical being. Let me now go even deeper into the mathematics of how the Higgs mechanism works, but in a way that does not require you to know any math. I want to explain the concept of gauge invariance and why it makes mass so problematic. Because this is really the heart of why the Higgs mechanism was needed in the first place. In physics, a gauge symmetry is a redundancy in how we describe nature. Think of it like this. You can describe the location of every city in the world using latitude and longitude. But your choice of where to put the zero line, the prime meridian, is arbitrary. You could put it through London, through Tokyo, through anywhere. The actual distances between cities do not change regardless of where you put your zero line. This freedom to choose your reference without changing the physics is analogous to gauge symmetry. In the standard model, gauge symmetry is not just a convenience. It is essential for the theory to be mathematically consistent. Without gauge symmetry, the theory produces nonsensical predictions. Infinite probabilities, negative probabilities, violations of conservation of energy. The theory only makes sense if gauge symmetry is maintained. But here is the problem. A mass term for a particle in the equations looks like a certain mathematical expression that explicitly breaks gauge symmetry. If you simply add mass to the particles by hand, by writing down that mathematical expression, gauge symmetry is violated and the theory breaks. This is why the standard model equations, in their gauge symmetric form, say that all particles must be massless. The genius of the Higgs mechanism is that it provides mass without explicitly breaking gauge symmetry. Instead, it breaks the symmetry spontaneously. The underlying equations remain perfectly gauge symmetric. But the ground state, the vacuum, the state of lowest energy, does not share this symmetry. The symmetry is hidden, not destroyed. And this hidden symmetry manifests as particle masses. It is like a dinner table set with perfect circular symmetry. Every place setting has a napkin to its left and a napkin to its right. The table is symmetric. But the moment the first guest picks up the napkin to their right, the symmetry is spontaneously broken. Now everyone must pick up the napkin to their right. The rule did not change. The table setting is still symmetric, but the actual state, who has which napkin, is not. This is spontaneous symmetry breaking. The Higgs field breaks the gauge symmetry of the standard model in exactly this way. The equations are symmetric, but the Higgs field has chosen a particular value, rolled down to a particular point on the brim of the Mexican hat, and in doing so has broken the symmetry and given particles their masses. I want to discuss something that connects the Higgs field to the very fabric of space and time. This is speculative, and I will clearly label it as such, but it is fascinating. Some theoretical physicists have explored the idea that the Higgs field might be connected to the geometry of space-time itself. In general relativity, Einstein's theory of gravity, the geometry of space-time is dynamic. It curves and warps in response to the presence of mass and energy. But what determines the properties of space-time at the quantum level? What gives space-time its structure? Some approaches to quantum gravity suggest that fields like the Higgs might play a role in determining space-time structure at the smallest scales. The Higgs field, with its non-zero value everywhere, contributes to the energy density of the vacuum, which in turn affects the curvature of space-time through Einstein's equations. In a universe without the Higgs field, the vacuum energy would be different, and the geometry of space-time would be different. There is also the intriguing question of whether the Higgs field might be connected to gravity in a more direct way. In the standard model, the Higgs field gives particles their inertial mass, the resistance to acceleration. General relativity tells us that inertial mass and gravitational mass are equivalent. This is the equivalence principle that Einstein used as the foundation of his theory of gravity. So in giving particles their inertial mass, the Higgs field is also, indirectly, determining how strongly they interact with gravity. Without the Higgs, particles would have no inertial mass, and therefore no gravitational mass, and would not curve space-time at all. They would not fall in gravitational fields. They would not attract other particles gravitationally. But I should be clear that the Higgs field does not directly generate gravity. Gravity is described by general relativity and involves the curvature of space-time itself. The Higgs field determines how much mass a particle has, and that mass then interacts with gravity through the usual way, by curving space-time. The Higgs is upstream of gravity, in a sense, but the two are separate phenomena. Let me now talk about the coupling constants, the numbers that determine how strongly each particle interacts with the Higgs field, and therefore how much mass each particle gains. These numbers are some of the most mysterious parameters in all of physics. The standard model has, depending on how you count, about 25 or 26 free parameters. These are numbers that the theory does not predict from any deeper principle. They must be measured experimentally and plugged into the equations by hand. Among these free parameters are the coupling constants of each particle to the Higgs field. These are sometimes called Yukawa couplings. The electron's Yukawa coupling is approximately 0.000003. Very small. This is why the electron is so light. The top quark's Yukawa coupling is approximately 1. This is why the top quark is about 350,000 times heavier than the electron. The neutrinos have Yukawa couplings so small that for years we thought they were zero, that neutrinos were massless. We now know they have tiny but non-zero masses, but their Yukawa couplings are at most about 1 trillionth. Why these specific values? Why is the top quark coupling to the Higgs field 350,000 times stronger than the electron's coupling? Why are there 3 generations of particles with masses that span such an enormous range? Nobody knows. There is no known principle that determines these numbers. They seem almost random, spanning many orders of magnitude without any obvious pattern. This is called the flavor puzzle, or the hierarchy of Fermion masses, and it is one of the deepest unsolved problems in particle physics. Many physicists believe that there must be some deeper structure, some more fundamental theory that explains these numbers. But we have not found it yet. Some theories propose that the Yukawa couplings arise from the geometry of extra dimensions. In string theory, for example, particles correspond to strings vibrating in different ways, and their couplings to the Higgs field depend on how they overlap in the extra dimensions. If the particles and the Higgs field are located at different positions in the extra dimensions, their overlap would be exponentially suppressed for some particles and not for others, naturally producing the observed hierarchy of masses. Other theories propose that the Yukawa couplings are generated dynamically, starting from some symmetric initial condition and then being modified by radiative corrections as you come down in energy from some high scale to the energies we observe. These are called radiative mass generation models. Still others propose that there is a new symmetry, a flavor symmetry, that relates the different generations of particles and constrains their Yukawa couplings. When this symmetry is broken, the Yukawa couplings take their observed values. All of these ideas are speculative, and none has been confirmed by experiment. The flavor puzzle remains open. Now let me talk about something that might surprise you. The Higgs boson has a spin of 0. It is the only known fundamental particle with 0 spin. Every other fundamental particle in the Standard Model has non-zero spin. Electrons, quarks, and neutrinos have spin 1/2. Photons, gluons, and the W and Z bosons have spin 1. The graviton, if it exists, is predicted to have spin 2. But the Higgs boson stands alone with spin 0. Why is this important? Because a particle's spin determines how its field behaves in spacetime. Spin 0 fields are called scalar fields. They are the simplest possible type of field. They have no direction, no polarization, just a simple number at every point in space. This simplicity is what allows the Higgs field to have a non-zero value in the vacuum. Fields with non-zero spin cannot easily have constant non-zero values in the vacuum because such values would pick out a direction in space, violating the symmetry of spacetime. But a scalar field has no direction to pick out. It can have a constant non-zero value without breaking the symmetry of spacetime. This is why the Higgs field can do what no other known field does. The discovery of the Higgs boson is also the first, and so far only discovery of a fundamental scalar particle. This is significant because many theories beyond the Standard Model predict other scalar particles. The inflaton field that drove cosmic inflation would be a scalar field. The field responsible for dark energy might be a scalar field. Many dark matter candidates involve scalar fields. The Higgs discovery proved that fundamental scalar fields exist in nature. They are not just mathematical constructions. Nature actually uses them. This gives us confidence that the other scalar fields predicted by theory might also be real. Let me now go into the weak nuclear force in more depth, because the Higgs mechanism's role in making the weak force short-range is one of its most important and often underappreciated consequences. The weak nuclear force is responsible for certain types of radioactive decay. It is the force that allows a neutron to transform into a proton, emitting an electron and an antineutrino in the process. This process, called beta decay, is essential for many things. It is essential for the nuclear reactions that power the sun. Inside the sun's core, protons are fused together to form helium, and some of these reactions require the weak force to convert protons into neutrons. Without the weak force operating correctly, the sun would not shine. The weak force is also responsible for the production of neutrinos, the ghostly particles that pass through matter almost without interacting. The Sun produces enormous numbers of neutrinos through weak force reactions, and these neutrinos stream outward through the Sun and across the universe. Billions of solar neutrinos are passing through your body right now, every second, without you feeling a thing. Now, the crucial point is that the weak force only operates over extremely short distances, roughly 1/1000th of the diameter of a proton. This is because its force carriers, the W and Z bosons, are very massive. And they are massive because of the Higgs field. The W bosons have a mass of about 80.4 billion electron volts. The Z boson has a mass of about 91.2 billion electron volts. These are enormous masses, roughly 80 to 90 times the mass of a proton. In quantum field theory, the range of a force is inversely proportional to the mass of its force carrier. A massless force carrier, like the photon, gives a force with infinite range. A massive force carrier gives a force with a very short range. The more massive the carrier, the shorter the range. Because the W and Z bosons are so heavy, the weak force has an incredibly short range. This is entirely due to the Higgs mechanism. If the Higgs field were turned off, the W and Z bosons would become massless, and the weak force would become a long-range force, identical in character to electromagnetism. In fact, it would reunify with electromagnetism into the single electroweak force. Every particle that feels the weak force would feel it over unlimited distances. Neutrinos, which currently interact so weakly that they can pass through light years of lead without stopping, would suddenly interact much more strongly and over much longer distances. The entire character of the universe would change. The fact that the weak force is short range has another profound consequence. It makes it possible for certain particles to be stable. Protons, for example, are stable in the Standard Model partly because the weak force is short range. If the weak force were long range, processes that could cause protons to decay might become possible. And the basic building blocks of matter would be unstable. Chemistry, biology, and life as we know it depend on protons being stable over timescales far longer than the age of the universe. Now let me address a question that often arises when people learn about the Higgs field. If the Higgs field is everywhere, if everything is immersed in it, if it has a constant non-zero value at every point in the universe, why do we not notice it? Why is there no obvious sign of this all-pervading field? The answer is precisely because it is constant and uniform. We cannot feel or detect something that is the same everywhere and never changes. Think of it this way. Fish cannot feel the water they swim in, not because the water is not there, but because they are always immersed in it. There is nothing to compare it to. There is no place where the water is absent for them to point to and say, there is the difference. Similarly, we cannot detect the Higgs field directly, because there is nowhere in the universe where its value is different. It is the same 246 billion electron volts everywhere. We are always immersed in it. We have never experienced anything else. The only way to detect it is to disturb it, to create a ripple in it, which is exactly what the LHC does when it produces a Higgs boson. The Higgs boson is a disturbance, a wave in the otherwise calm, uniform Higgs field. And detecting that disturbance is how we prove the field exists. This is a general principle in physics. Constant, uniform backgrounds are invisible to direct detection. Only changes, variations, disturbances are detectable. The Higgs field in its ground state is as invisible as the water is to fish. But just as water reveals itself when you create waves, the Higgs field reveals itself when you create Higgs bosons. Let me now discuss the history of the discovery in more detail. Because it is a remarkable story of human perseverance, international collaboration, and scientific dedication spanning decades. The theoretical prediction of the Higgs mechanism was made in 1964, but the technology to test it did not exist for decades. The problem was that nobody knew exactly how heavy the Higgs boson would be. The theory predicts its existence and its properties, but not its mass. The mass depends on a parameter in the Higgs potential that can only be determined by measurement. So experimenters had to search a wide range of possible masses. The first serious search began at the Large Electron-Positron Collider, also at CERN, which operated from 1989 to 2000. This machine explored Higgs masses up to about 114 billion electron volts and found nothing. But it set a lower limit. The Higgs, if it existed, had to be heavier than 114 billion electron volts. Meanwhile, the Tevatron at Fermilab in the United States, operating from 1987 to 2011, searched for the Higgs at higher masses. It was able to exclude certain mass ranges, but did not have quite enough energy or data to make a discovery in the mass range where the Higgs actually turned out to be. Then came the LHC, which began operations in 2008. After a setback in its first year involving a faulty electrical connection that caused significant damage, the machine was repaired and began taking physics data in 2010. Within just 2.5 years, by July 2012, it had accumulated enough data to discover the Higgs boson. The speed of this discovery was remarkable and reflects both the incredible performance of the machine and the extraordinary skill of the thousands of physicists analyzing the data. The discovery announcement on July 4, 2012 was one of the great moments in the history of science. It was broadcast live around the world. The auditorium at CERN was so packed that people had camped outside overnight to get seats. The presentation showed the data clearly. A bump in the invariant mass distribution at about 125 billion electron volts, seen independently by both ATLAS and CMS. The statistical significance was overwhelming. It was real. It was there. The Higgs field exists. Since that day, the LHC has produced and studied tens of millions of Higgs bosons, and our knowledge of this particle has grown enormously. We now know its mass with a precision of about 0.1%. It is 125.1 plus or minus 0.14 billion electron volts. We have measured its decay rates into photon pairs, into W boson pairs, into Z boson pairs, into bottom quark pairs, and into tau lepton pairs. All are consistent with standard model predictions. We have measured how it is produced through various mechanisms involving gluons, W and Z bosons, and top quarks, all consistent with the standard model. In 2018, a major milestone was reached when both ATLAS and CMS directly observed the Higgs boson's coupling to the top quark, the heaviest known particle, and to the bottom quark and the tau lepton. These measurements confirm that the Higgs mechanism works as predicted for the third generation of particles. In 2022, another milestone was reached with evidence for the Higgs boson decaying to muon pairs. Muons are second-generation particles, lighter than tau leptons, and their coupling to the Higgs is accordingly weaker. Seeing this rare decay mode confirmed that the Higgs mechanism works for the second generation as well. The first generation, which includes the up and down quarks and the electron, has the weakest coupling to the Higgs, and directly observing Higgs decays to these particles is beyond the reach of current experiments. The rates are simply too low compared to the backgrounds. But the pattern is clear. The Higgs boson couples to particles in proportion to their mass, exactly as the theory predicts. Let me now explore an area that pushes into the frontier of current research. One of the most important measurements that the LHC is currently pursuing is the d-Higgs production cross-section. This means producing two Higgs bosons simultaneously in a single collision. Why is this so important? The reason is that d-Higgs production is sensitive to the Higgs self-coupling, the strength with which the Higgs boson interacts with itself. The Higgs self-coupling determines the shape of the Higgs potential near its minimum. It tells us about the curvature of that Mexican hat shape at the point where the ball is resting. If the self-coupling deviates from the standard model prediction, it could indicate new physics and could change our understanding of vacuum stability. D-Higgs production is extremely rare. The standard model predicts it happens about 1,000 times less often than single Higgs production. At the current LHC, detecting this process is at the very edge of possibility. The high luminosity LHC upgrade, expected to operate through the 2030s, will collect about 20 times more data than the LHC has collected to date, and should be able to observe D-Higgs production and make a first measurement of the self-coupling. This will be one of the most important measurements in particle physics in the coming decade. If the self-coupling turns out to be different from the standard model prediction, it would be revolutionary. It could point to new particles, new forces, or new symmetries that modify the Higgs potential. It could change our understanding of whether the vacuum is stable or metastable. It could provide clues about the hierarchy problem. The stakes are enormous. Now I want to take you through something truly remarkable about the Higgs field. Its role in the mass of the W and Z bosons is not just about making them heavy. The Higgs mechanism actually determines the relationship between the W mass and the Z mass, and this relationship has been tested to extraordinary precision. In the standard model, the ratio of the W mass to the Z mass is determined by a parameter called the weak mixing angle. This angle describes how the original electroweak force carriers mix to produce the W, Z, and photon that we observe. The Higgs mechanism makes specific predictions about these masses and their relationship. The Z boson should be heavier than the W boson by a specific amount determined by the weak mixing angle. This prediction has been confirmed experimentally to remarkable precision. In fact, the precision measurements of the W mass, the Z mass, and the weak mixing angle are so accurate that they were used to predict the mass of the top quark before it was discovered. The top quark, through quantum loop effects, slightly shifts the values of these parameters. By measuring the parameters precisely and comparing with theory, physicists predicted in the early 1990s that the top quark should have a mass of approximately 170 billion electron volts. When the top quark was discovered at Fermilab in 1995, its measured mass was 174 billion electron volts. This was a spectacular confirmation of the standard model and of the Higgs mechanism. Similarly, the precision measurements were used to predict the approximate mass of the Higgs boson itself before it was discovered. They pointed to a Higgs mass in the range of about 100 to 200 billion electron volts, with the best fit around 120 billion electron volts. The discovery at 125 billion electron volts was in perfect agreement. The internal consistency of the standard model, with the Higgs mechanism at its heart, is truly remarkable. Let me now discuss the energy scale of the Higgs mechanism and what it tells us about the universe. The Higgs field value of 246 billion electron volts sets what physicists call the electroweak scale. This is the energy scale at which the electromagnetic and weak forces become unified. Below this energy, they appear as separate forces with different strengths and ranges. Above this energy, they merge into a single electroweak force. The electroweak scale is enormously higher than the energies we experience in everyday life. The thermal energy of atoms at room temperature is about 1/40th of an electron volt. Chemical bond energies are a few electron volts. Nuclear energies are a few million electron volts. The electroweak scale is 246 billion electron volts. It is a million times higher than nuclear energies and hundreds of billions of times higher than everyday energies. Yet it is far, far below the Planck scale of 10 to the 19th billion electron volts, where quantum gravity becomes important. The Electroweak scale sits in the middle of this enormous range, and why it sits where it does is essentially the hierarchy problem we discussed earlier. At the LHC, we are probing the Electroweak scale directly. We are creating collisions with enough energy to access this regime, to excite the Higgs field, to produce W and Z bosons freely. This is why the LHC was built, to explore the physics at and around the Electroweak scale, and to understand the mechanism that breaks the Electroweak symmetry. Now let me take you to an area of current research that is particularly exciting. It involves the question of whether the Higgs boson we discovered is truly elementary, or whether it might be composite, made of something smaller. In the history of physics, particles that were once thought to be elementary have often turned out to be composite. Atoms were thought to be fundamental until we discovered they are made of protons, neutrons, and electrons. Protons and neutrons were thought to be fundamental until we discovered they are made of quarks. Could the Higgs boson be next? Could it be made of smaller, more fundamental constituents? This is not just idle speculation. There are good theoretical reasons to consider this possibility. The hierarchy problem, which we discussed earlier, might be solved if the Higgs boson is not elementary but composite. If the Higgs is made of more fundamental particles bound together by a new force, then its mass would naturally be of the order of the energy scale at which this new force operates. There would be no fine-tuning problem because the Higgs mass would be determined by the dynamics of this new force, just as the proton mass is determined by the dynamics of the strong force. These theories are called composite Higgs models or Technicolor models in their various incarnations. They predict new heavy particles at energies somewhat above the Electroweak scale, new force carriers mediating the binding of the Higgs constituents. The LHC has searched extensively for such particles and has not found them, which puts strong constraints on these models. But they are not entirely ruled out. The new particles could be heavier than the LHC can produce. Future colliders with higher energies would continue this search. Currently, all measurements of the Higgs boson's properties are consistent with it being elementary. It behaves exactly as a point-like, structureless particle should. But the measurements are not infinitely precise, and there is room for small deviations from the elementary prediction. More precise measurements at the high luminosity LHC and at future colliders will continue to test this question with increasing sensitivity. Let me now explore the connection between the Higgs field and neutrino masses. Neutrinos are among the most mysterious particles in the Standard Model. For decades, they were assumed to be massless. The original Standard Model was formulated with massless neutrinos, but experiments in the late 1990s and early 2000s showed that neutrinos do have mass, albeit incredibly tiny. The heaviest neutrino has a mass of at most about 1/10 of an electron volt, which is less than a millionth of the electron mass. The question of how neutrinos get their mass is one of the biggest open questions in particle physics. In the original Standard Model, fermions get their mass through the Higgs mechanism by having both left-handed and right-handed components that are coupled by the Higgs field. But here is the puzzle. Only left-handed neutrinos have ever been observed. No right-handed neutrino has ever been detected. If right-handed neutrinos do not exist, then neutrinos cannot get mass through the standard Higgs mechanism. There are several possible solutions. One is that right-handed neutrinos do exist, but are very heavy, far heavier than anything we can produce at current colliders, and have no interactions except gravity and the Higgs coupling. These are called sterile neutrinos. The interplay between the sterile neutrino mass and the Higgs mechanism can produce the tiny observed neutrino masses through what is called the seesaw mechanism. The heavier the sterile neutrino, the lighter the observed neutrino. If the sterile neutrinos have masses around 10 to the 15th billion electron volts, near the scale where the three forces of the standard model might unify, then the observed neutrinos would naturally have masses in the correct tiny range. Another possibility is that neutrinos get mass through a different kind of Higgs mechanism involving a different Higgs field. Some models introduce a second Higgs field, called the Type 2 seesaw, where a new Higgs particle with different quantum numbers gives mass directly to neutrinos. Yet another possibility is that neutrinos are their own antiparticles, so-called Majorana particles, and their mass arises through a different mathematical mechanism that does not require the standard Higgs coupling. The truth is, we do not know how neutrinos get their mass. It might involve the Higgs field we have discovered, it might involve a new Higgs field, or it might involve something entirely different. This is one of the most active areas of research in particle physics today. Let me now talk about something that connects the Higgs field to the everyday world in a way that most people do not realize. The Higgs field determines the masses of quarks and leptons, and these masses determine the properties of atoms and molecules. The specific masses that nature has chosen, through whatever mechanism determines the Yukawa couplings, are responsible for the specific chemistry that exists in our universe. Consider hydrogen, the simplest atom. It consists of one proton and one electron. The binding energy of this atom, how much energy it takes to pull the electron away, depends on the masses of both the electron and the proton. If the electron were heavier, it would orbit closer to the proton, and the atom would be smaller and more tightly bound. If the electron were lighter, it would orbit farther away, and the atom would be larger and more loosely bound. The specific electron mass that the Higgs field provides gives hydrogen its specific size and binding energy. Now consider nuclear physics. The neutron is slightly heavier than the proton by about 1.3 million electron volts. This tiny mass difference, which ultimately comes from the difference in mass between the down quark and the up quark, both masses provided by the Higgs field, has enormous consequences. Because the neutron is heavier than the proton, free neutrons are unstable and decay into protons. But protons are stable. This means hydrogen is stable. If the mass difference were reversed, if the proton were heavier than the neutron, then protons would decay and hydrogen would not exist. No hydrogen means no water, no organic chemistry, and no life as we know it. Even more subtly, the specific value of the neutron-proton mass difference determines which nuclei are stable. It determines the nuclear physics of stellar interiors, which nuclei can fuse, which elements are produced. The entire periodic table of elements, with all its chemistry, ultimately traces back to quark masses provided by the Higgs field. Carbon, the element essential for all known life, is produced inside stars through a process called the triple alpha process, where 3 helium nuclei fuse to form carbon. This process is extraordinarily sensitive to nuclear physics parameters, which in turn depend on quark masses. If the up or down quark masses were even slightly different, the triple alpha process might not work. Carbon might not be produced in stars, and life as we know it could not exist. So when you ask what the Higgs field is actually doing to every particle around you, the answer is not just giving them mass. It is, through the specific masses it assigns, determining the entire structure of the physical world. It is determining which atoms are stable, which chemical bonds are possible, which nuclear reactions work, which elements exist. The Higgs field is not just responsible for mass. Through mass, it is responsible for the structure of reality. Let me now address a question that comes up frequently. Is the Higgs field the same as dark energy? The short answer is no, but the relationship between them is complicated and mysterious. Dark energy is the name we give to whatever is causing the expansion of the universe to accelerate. Observations tell us that about 68% of the total energy content of the universe is in this form. It behaves like a constant energy density, filling all of space, pushing space apart at an ever-increasing rate. The Higgs field, with its non-zero value, does contribute to the vacuum energy density. When the Higgs field settled into its current value, it lowered its potential energy. But quantum field theory tells us that the absolute energy of the vacuum should include contributions from many sources, including all the quantum fields and their fluctuations. The Higgs contribution to the vacuum energy is one piece of a very complicated puzzle. The mystery is that the observed value of the vacuum energy, what we call the cosmological constant, is about 120 orders of magnitude smaller than what quantum field theory naively predicts. This is the cosmological constant problem, and it is one of the greatest unsolved mysteries in physics. The Higgs field is part of this puzzle because it contributes to the predicted vacuum energy, but the real problem is much deeper than any single field. It involves our fundamental understanding of how quantum mechanics and gravity work together. So no, the Higgs field is not dark energy. But the Higgs field contributes to the theoretical vacuum energy that is so puzzlingly different from the observed dark energy. Solving this puzzle may require understanding quantum gravity, which is itself one of the greatest challenges in theoretical physics. Now I want to take you even deeper into the nature of the Higgs field and discuss the concept of the Higgs vacuum. In quantum field theory, the vacuum is not empty. It is filled with quantum fluctuations. Virtual particles constantly appear and disappear. Fields fluctuate around their ground state values. The vacuum is a seething, dynamic entity at the quantum level. For most fields, the ground state value is zero. The fluctuations happen around zero. But for the Higgs field, the ground state value is not zero. It is 246 billion electron volts. The quantum fluctuations of the Higgs field happen around this non-zero value. This is what makes the Higgs vacuum unique among all quantum field vacua. When we produce a Higgs boson at the LHC, what we are really doing is creating a fluctuation of the Higgs field away from its ground state value. The Higgs boson is a temporary disturbance, a small vibration around the non-zero vacuum value. It quickly relaxes back, decaying into other particles and transferring its energy. But for that brief moment, the Higgs field at one point in space has a slightly different value than it does everywhere else. That local disturbance is the Higgs boson. This perspective helps us understand why the Higgs boson's properties are so tightly connected to the Higgs field's vacuum properties. The mass of the Higgs boson is determined by the curvature of the Higgs potential at the minimum. How easily can you disturb the field? How quickly does it want to return to its equilibrium value? A stiff potential with high curvature gives a heavy Higgs boson. A shallow potential with low curvature gives a lighter Higgs boson. The measured mass of 125 billion electron volts tells us the curvature of the Higgs potential. And from this, combined with measurements of the self-coupling, we can reconstruct the entire shape of the potential. Let me now discuss something that bridges the gap between the abstract world of particle physics and the concrete world of technology and application. You might wonder whether our understanding of the Higgs field will ever have practical applications. The honest answer is that direct applications are unlikely in the foreseeable future. The Higgs boson is incredibly difficult and expensive to produce, and it decays almost instantly. There is no obvious way to harness it for practical purposes. However, the history of fundamental physics research is filled with examples of discoveries that seemed purely academic at the time, but later led to transformative technologies. When Maxwell unified electricity and magnetism in the 1860s, no one imagined radio, television, or wireless communication. When Einstein described the photoelectric effect in 1905, no one imagined solar cells. When physicists studied the quantum mechanics of semiconductors in the 1940s, no one imagined the computer revolution. The transistor, the laser, nuclear energy, Mri machines, GPs, the World Wide Web, all of these came from fundamental research that had no obvious practical application at the time. The LHC itself has already produced significant technological spin-offs. The superconducting magnet technology developed for the LHC has applications in medical imaging and energy storage. The data processing techniques developed to handle the enormous data volumes have contributed to cloud computing and big data analytics. The particle detector technologies have applications in medical imaging, security screening, and materials science. The World Wide Web itself was created to solve a data-sharing problem at CERN. So while we cannot predict what practical applications might eventually come from understanding the Higgs field, history tells us that fundamental understanding of nature has always, eventually, led to technological progress. The Higgs field teaches us something deep about how mass works at the most fundamental level. Who knows what humanity might eventually do with that knowledge? Let me now take a step back and synthesize everything we have discussed, because I want to make sure you have a complete picture of what the Higgs field is doing to the universe around you. Picture the universe about 13.8 billion years ago. It is less than 1 trillionth of a second old. It is incredibly hot, far hotter than the center of any star. At this temperature, the Higgs field has a value of 0. All fundamental particles are massless. Everything is moving at the speed of light. There are no atoms, no nuclei, no structure of any kind. The electromagnetic force and the weak force are unified into a single electroweak force. The W and Z bosons are massless, just like the photon. Quarks and leptons are massless. The universe is a symmetric, featureless soup of massless particles and radiation. Then, as the universe expands and cools, it reaches a critical temperature, about 10 to the 15th degrees, roughly 100 million times hotter than the center of the sun. At this temperature, the Higgs field undergoes its phase transition. Like water suddenly freezing into ice, the Higgs field suddenly acquires its non-zero value throughout all of space. In that instant, the symmetry breaks. The W and Z bosons acquire their masses, and the weak force becomes short-range. Quarks and leptons acquire their masses and can now move at less than light speed. The electromagnetic and weak forces separate into the two distinct forces we observe today. From this moment forward, the universe can develop structure. Quarks, now massive, can be bound by the strong force into protons and neutrons. Electrons, now massive, can be captured into orbits around nuclei to form atoms. Atoms can form molecules. Molecules can form gas clouds. Gas clouds can collapse under gravity to form stars. Stars can forge heavier elements in their cores. Those elements can form planets. On those planets, chemistry can become biology. And biology can become you. All of this traces back to that one moment when the Higgs field switched on. Every atom in your body, every molecule in your cells, every chemical reaction that keeps you alive, exists because the Higgs field has a non-zero value throughout space. You are, in the most literal and physical sense, a child of the Higgs field. And what is the Higgs field doing right now, at this very moment? It is maintaining its constant non-zero value at every point in space around you. It is continuously interacting with the quarks and electrons in your body, giving them their masses, giving them the inertia they need to form stable atoms, stable molecules, stable structures. It is ensuring that the W and Z bosons remain heavy, that the weak force remains short-range, that the nuclear physics that powers the sun continues to work correctly. The Higgs field is not doing anything dramatic right now. It is not fluctuating wildly or creating exotic particles. It is just being there, constant, uniform, ever present. And in that quiet, constant presence, it is holding the entire physical world together. Without it changing, without it doing anything noticeable, its mere existence enables everything you see, touch, and experience. Now let me discuss the future of Higgs physics and what the coming decades might bring. The high-luminosity LHC, scheduled to begin operations in the late 2020s, will collect about 20 times more data than has been collected so far. This will allow much more precise measurements of Higgs boson properties. Any small deviation from standard model predictions could point to new physics. The HLLHC will also make the first measurement of the Higgs self-coupling, telling us about the shape of the Higgs potential. Beyond the HLLHC, several future collider projects are under discussion. The proposed future circular collider at CERN would first operate as an electron-positron collider optimized for Higgs production, measuring Higgs properties with unprecedented precision. It would then be upgraded to a proton-proton collider at energies far beyond the LHC. The timeline for this project stretches into the 2050s and beyond. The cost is estimated at over $20 billion. The decision on whether to proceed is one of the most important facing the particle physics community. China has proposed the Circular Electron-Positron Collider, a similar machine that would function as a Higgs factory. Japan has proposed the International Linear Collider, a linear electron-positron machine. In the United States, there are discussions about next-generation collider technologies, including muon colliders, which could achieve very high energies in a relatively compact machine. All of these projects share a common goal: to study the Higgs sector in more detail than ever before. We want to know if the Higgs is truly elementary or composite. We want to measure its self-coupling. We want to search for additional Higgs bosons. We want to look for any sign of new physics connected to the electroweak symmetry breaking mechanism. The Higgs boson, while discovered, remains poorly understood in many ways. We have found the particle, but we have not fully understood its implications. There is also an exciting possibility that future gravitational wave experiments could detect signals from the electroweak phase transition itself. If the transition was first order, as some models predict, it would have produced gravitational waves with frequencies that might be detectable by space-based gravitational wave observatories like the proposed LISA mission. Detecting these waves would give us direct information about the Higgs mechanism at the moment it first operated, just a trillionth of a second after the Big Bang. We would be hearing the echo of the moment mass was born. Let me now explore one more deep connection that is worth understanding: the Higgs field and the concept of symmetry. Symmetry is arguably the most powerful concept in all of physics. The laws of physics are built on symmetries. Conservation of energy comes from the symmetry of time. The fact that the laws of physics are the same today as yesterday. Conservation of momentum comes from the symmetry of space. The fact that the laws of physics are the same here as there. Conservation of electric charge comes from a more abstract symmetry, a gauge symmetry of the electromagnetic field. The standard model is built on a specific set of gauge symmetries. These symmetries dictate everything about the theory. They determine what particles exist, what forces exist, and how particles interact with each other. They are not optional decorations. They are the very foundation on which the theory is built. The Higgs mechanism is all about the relationship between the symmetry of the laws and the symmetry of the ground state. The laws of physics are perfectly symmetric under the electroweak gauge symmetry. But the ground state, the vacuum, is not symmetric. The Higgs field has chosen a direction, broken the symmetry. And it is this mismatch between the symmetry of the laws and the asymmetry of the vacuum that gives particles their masses. This pattern, symmetric laws with a non-symmetric ground state, appears throughout physics. Magnets are made of iron atoms whose magnetic properties are governed by symmetric laws. But below a certain temperature, the magnets spontaneously align, pointing in one direction, breaking the symmetry. Crystals form from atoms governed by symmetric forces. But the crystal lattice picks out specific directions, breaking the rotational symmetry. The Higgs mechanism is the same idea applied to the universe itself. The laws are symmetric. The universe is not. And in the gap between symmetric laws and an asymmetric universe, everything interesting happens. Let me discuss one more fascinating aspect of the Higgs boson that is not widely known. The Higgs boson is unstable, as I mentioned, with an incredibly short lifetime. But the way it decays tells us something profound about the interconnectedness of particle physics. The Higgs boson can decay in many different ways. It can decay into 2 photons, 2 Z bosons, 2 W bosons, 2 bottom quarks, 2 tau leptons, 2 muons, and potentially other particles. The probability of each decay mode is precisely predicted by the Standard Model and depends on the coupling strength of each particle to the Higgs field. Heavier particles couple more strongly, so the Higgs preferentially decays to the heaviest particles that it has enough mass to produce. The most common decay is to a bottom quark and an anti-bottom quark pair, happening about 58% of the time. This is because the bottom quark is the heaviest particle, lighter than half the Higgs mass. The decay to W boson pairs happens about 21% of the time. The decay to gluon pairs, which happens through a top quark loop, since gluons do not directly couple to the Higgs, occurs about 9% of the time. The decay to tau lepton pairs occurs about 6% of the time. The rare decay to 2 photons occurs only about 0.2% of the time. Interestingly, the decay to 2 photons was one of the main channels through which the Higgs was discovered, despite being so rare. This is because photons are very clean experimentally. They leave clear signals in the detector with precise energy measurements, and the backgrounds are relatively small. The common decay to bottom quarks, while frequent, is much harder to identify because quarks produce messy jets of particles that can easily be confused with background processes. The decay to 2 photons is also theoretically fascinating because it cannot happen directly. The Higgs boson does not couple to photons because photons are massless. Instead, this decay proceeds through virtual loops of heavy particles, primarily top quarks and W bosons, that do couple to both the Higgs and the photon. The rate of this rare process depends sensitively on what heavy particles exist in nature. If there are new heavy charged particles beyond the Standard Model, they would contribute to the loop and change the rate. This makes the Higgs to 2 photons rate a sensitive probe of new physics. So far, all measurements of Higgs decay rates agree with Standard Model predictions within experimental uncertainties. But the uncertainties are still several percent in many cases. Future experiments will push these uncertainties down to the sub-percent level, providing an incredibly sensitive test of the Standard Model and potentially revealing the first signs of physics beyond it. Now let me bring us to one of the most philosophically profound aspects of the Higgs story. The universe, at its deepest level, appears to be built from mathematics. The Higgs mechanism was predicted purely from mathematical considerations. Peter Higgs and others did not observe anything experimentally and then try to explain it. They started from the mathematics of gauge symmetry, noticed a problem with mass, and proposed a mathematical solution. Decades later, an enormous machine confirmed that nature actually works this way. This raises deep questions about the relationship between mathematics and physical reality. Why should the universe obey mathematical laws at all? Why should a mathematical prediction about an invisible field turn out to correspond to something real? This is a question that has puzzled physicists and philosophers for centuries. Eugene Wigner, a Nobel laureate physicist, wrote a famous essay in 1960 titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," in which he marveled at the fact that abstract mathematics, developed without any reference to the physical world, repeatedly turns out to describe physical reality with extraordinary precision. The Higgs mechanism is one of the most dramatic examples of this unreasonable effectiveness. A mathematical requirement, gauge symmetry, combined with a mathematical solution. Spontaneous symmetry breaking predicted the existence of an entirely new field permeating all of space, and 48 years later, experiment confirmed it. The mathematics was not just a description of reality. It was a guide to reality. It told us something was there before we could see it, before we could detect it, before we had any experimental evidence for it. And it was right. This should fill you with a sense of awe. We live in a universe whose deepest structures can be predicted by mathematics. The Higgs field, invisible and undetectable by any everyday means, was found because mathematics said it had to be there. What else might mathematics be telling us about reality that we have not yet confirmed? Dark matter? Extra dimensions? The multiverse? The deepest truths about the universe may still be hidden in equations that we have not yet written down, or in equations that we have written down but cannot yet test. Let me take you now through the full picture of how the standard model of particle physics looks, with the Higgs mechanism at its center.